So we will start with a problem. So you can see that there are two circuits which is shown in figure A and figure B. Okay, and there is a voltage which is given, that is known as V bias, which is given shown here, which is of 10 volt, which is given to a diode. Okay, and the question is to find the current. Okay, so the question is to find the current. So you can read the question carefully, that is to find the current. So you can see that this is the positive of the battery and this is the negative of the battery, and this is the p-type semiconductor and this is the n-type semiconductor. So the first figure actually showing that the positive of the battery is connected to the p-type semiconductor and the negative of the battery is connected to the ground, you can see here, and this is also ground. That means both grounds are connected, these are all connected here. That means the negative is connected to the n-type semiconductor, so you can say that it is forward bias. Okay, now in the second case you can see the positive of the battery is connected to the n-type semiconductor and the negative of the battery is connected to the p-type semiconductor. That means the positive is connected to n and the negative is connected to the p. That means it is reverse bias. Okay, so the first figure, figure A, is forward biased. The circuit is forward biased, and the second figure actually it is showing a reverse biased diode. Okay, so we will first start with the question A. You have to determine the forward voltage and the current for the diode for each diode models. Okay, so first of all we will consider the part A. Okay, we will consider the part A, we will consider the part A of the problem. So we will consider the ideal model first. In the ideal model, you know that the diode can be replaced with the short circuit, right? Because I will take the first part A. So you have the circuit like this. This is the R limit and you are having a diode here, right? And this is the V bias, which is of 10 volt. It is connected, all are connected to the ground. Now you see I am going to apply the ideal model for the diode. For the ideal model, you see this circuit is forward bias. So we can say that the diode can be replaced with a short circuit. That is the case in the forward bias for the ideal model. So this is 10 volt. I have the resistance R limit, and the diode I am going to replace with a short circuit. Now this is my short circuit. So I can say that the current IF, the forward current here, IF is nothing but the V bias, that means 10 volt divided by your R limit, and R limit is given as 1 kilo ohm, so you will get it as 10 milliampere. Okay, that's it. Now what will be the voltage across the resistance? The voltage across the resistance, since the current is moving like this, so you can say that the current is moving like this, so this end become positive and this end become negative, and you know the voltage across the R limit is nothing but the current IF into R limit. That means the current is 10 milliampere into 1 kilo ohm, that means 10 volt. So whatever you are applying using the battery, that 10 volt will be dropped across the R limit. Okay, so this is the ideal model. Next we will consider the practical model. Okay, so in the practical model, you know that in the practical model the diode can be replaced with, if the diode is forward bias, during the forward bias, okay, this is also for the forward bias, the diode can be replaced with a positive negative. That means this is your p-type side and this is the n side, and a short circuit. Okay, this is a short circuit also. So I am going to replace the diode with this model. So I have the 1 kilo ohm resistance and I have 10 volt battery. Now I am going to replace the diode with the model. That means I have a positive negative. This is p-type. Okay, and a short circuit. This is the short circuit. So this is 0.7. We have already discussed this thing. Now this is 10 volt. So you can write the Kirchhoff law here. You are starting from the minus, this is plus. The current is moving like this, that means it is plus and minus, and you know this is plus and this is minus. So I will start from here. Okay, I will start from here. So it is minus 10 volt. Okay, then you see here this is plus, so plus IF. I don't know what is the current. I will say it is IF into 1 kilo, right? 1 kilo ohm. Then again you see here it's plus, so plus 0.7 is equal to 0. Okay, so you can see IF is nothing but 9.3 volt divided by 1 kilo. If you solve this equation, you will get it's 9.3 volt, sorry, milliampere. Okay, milliampere. So that will be the IF. So you got the equation for IF. Now you can find the voltage across the R limit. It is nothing but IF. That means the voltage here. I am talking about the voltage across the resistance. This is known as VR limit. That means IF into R limit. That means 9.3 milliampere into R limit is 1 kilo ohm, which is equal to 9.3 volt. Okay, so that's the practical model. That's how you can solve by using practical model in forward bias condition. Now we have another condition, that means another thing which is known as the complete model. Complete model. So in the complete model, you can say that we have the diode which can be replaced with, this is the P type and this is 0.7 volt. You have the short circuit with a RD dash. Okay, and in the question you can see, in the question the RD dash is given which is 10 ohms. So you can include it, which is 10 ohms. Okay, now I will in forward bias. Okay, this is the case with forward bias. Now I can say here this is my R limit, which is 1 kilo ohm, and this is 10 volt. I have the diode. I am going to replace the diode with plus minus and RD dash. Okay, plus minus 0.7 and RD dash as 10 ohms. Okay, now you see this is your IF. Okay, so you can write the Kirchhoff law. Since the IF is passing like this, moving like this, this is plus minus. Okay, and this is plus minus and this is plus minus. So you can start from here. So it's minus 10 volt, then plus IF into R limit. Okay, plus 0.7 plus, you see this current is going down, so this is plus and this is minus, plus IF into RD dash, this is equal to 0. That means this is minus 10 volt plus IF into 1 kilo ohm plus 0.7 plus IF into what is RD dash is 10 ohm, this is equal to 0. So what is IF? It is 9.3 divided by 1 kilo ohm plus 10 ohms. Okay, so you will get the current as 9.21 milliampere. Okay, now you can calculate the voltage across the R limit here. This is the voltage across the R limit as IF into R limit. This is nothing but 9.21 milliampere into 1 kilo. That means it's nothing but 9.21 volt. So this kind of problems you can expect for the exam. We will do some more problems. This is very easy problem anyway, so we will include more problems also. Now we will see the case B. Okay, our case B. Okay, this is our case B. Okay, we have already explained the case A. Now we will see what is case B. In the case B, you know the circuit is like this. This is 10 volt, this is 1 kilo, but the diode was connected like this. You can see this is reverse bias. Okay, reverse bias, I have already explained this. So in reverse bias, we will talk about the ideal model. In ideal model, the reverse bias condition says that it's open circuit. You have an open circuit. So what is the current IF? IF will be equal to 0 because it's reverse bias. It's open circuit. That means you can have the circuit like this, 1 kilo. This is 10 volt and open circuit. Okay. You can see like this. It's an open circuit. You can represent like this also, no problem. Okay. Now you see it's open circuit, so IF equal to 0. So the voltage across the R limit is nothing but IF into R limit, which is nothing but how much? It will be equal to 0 volt. Now we have another model that is known as the practical model. In the practical model, in reverse bias, this case 1, this is 2. In the reverse bias, the practical model is also open circuit. So again you will get IF equal to 0 and the voltage across R limit become IF into R limit. That means again it's 0 volt. Okay. Next we have the last part, that is the complete model for the reverse bias. Complete model for the reverse bias is like a open circuit, but there is a small leakage through a large resistance, and this resistance we will usually denote it as RR dash. Okay, this is the complete model. Now we will see what is this RR dash from the question. You can see from the question the RR dash is not given, but it is given that the leakage current is 1 microampere, right? It is given that leakage current is 1 microampere. So the leakage current is given, leakage current, which is 1 microampere. Okay, that is the leakage current. That means you have a circuit like this. This is your circuit. Your diode is reverse bias. This is 1 kilo and the diode is reverse bias. So I can represent like an open circuit and a resistance, and this is okay. Now there is a current which is the leakage current. The current will always flow from positive to negative, so the leakage current will be like this. But for the diode it is N and this is P. So for the diode the leakage current is flowing from N to P. Okay, and this current actually it has been given as this current, small current which is flowing like this, and this current is given as 1 microampere. Now you can have, this is 1 kilo ohm, then you can find all these voltages. Now you see here this is 10 volt and 1 kilo is there for the resistance. You can write the Kirchhoff law, that is minus 10. Okay, minus 10. Then the reverse current, that means the reverse current is, you know, the reverse current is flowing like this, so it is plus minus, so plus 1 microampere into 1 kilo ohm. Okay, plus plus you don't know about the resistance R dash. Okay, RR dash into 1 microampere. This is equal to 0. You can find RR dash also. Okay, so this is one of the equation. So you can get the RR dash is equal to 10 minus 1 microampere into 1 kilo ohm divided by 1 microampere. This is the value of RR dash. It's very easy to find the RR dash. Now you can find the voltage across the R limit. It's equal to, only this is asked for the question. This is, I have given you some extra information. So in the question it is asked to find the voltage across the R limit, that is nothing but 1 microampere is the current into 1 kilo ohm. Okay, that is the resistance. So it was equal to 1 millivolt. Okay, now the voltage across the diode. What is the voltage across the diode here? The voltage across the diode here, you know that this voltage is 1 millivolt. Then you have applied 10 volts. Then how much will be the voltage here? The voltage is nothing but 10 minus 1 millivolt. This is nothing but 9.999 volt. Okay, this is the case. Similarly, what is the voltage across the diode here? In this case, the voltage across the diode, you are applying here 10 volt, and the voltage across this resistance is 0 volt. So according to the Kirchhoff law, this will be 10 volt, right? Similarly, for the practical model, also the voltage across the diode, voltage across diode is again 10 volt, because there is no voltage drop across the resistance. Similarly, for the forward bias condition, what is the resistance across the what is the voltage across the diode here? This is the diode. The voltage across the diode, voltage across the diode, it is a short circuit. That means the voltage is 0 volt. Similarly, in the practical model, you can see the voltage across the diode is the voltage across the diode. This is the voltage across the diode. Across the diode is again you can see it's 0.7 volt, right? It is 0.7 volt. What is the voltage across the diode in the complete model? In the complete model, this is your diode actually. So this voltage is nothing but your 0.7 plus the current, you know, IF into RD dash. That means it is nothing but 0.7 plus IF is 9.21 milliampere and RD dash is 10 ohm, I think. Yeah, 10 ohm. So you can find the voltage across the diode as 0.792. That's it. Or you can say 792 millivolt. That is the voltage across the diode. So this is how to solve this problem. This is the complete analysis of this problem, complete solution for this problem. Okay, so next we will see one of the important application of the diode, and you know that a diode is having, I will just conclude regarding the characteristics of diode. So a diode is giving you, we usually used to use the practical model for the diode in many situations. So from now onwards I will be using the practical model for the diode. So I will just give you a small review on this practical model for the diode. You know that this is the symbol for the diode, and in the forward bias, this is the P type and this is the N type. In the forward bias, we will connect the diode with a positive here and a negative here of the battery, and that means this is P and this is N. Is P is connected to the positive and N is connected to the negative. So what we can expect a current, and in practical model I told you there is a voltage across the diode which has 0.7. it will be like this, 0.7 volt. And in reverse bias, your diode will act like an open circuit. That means the current is equal to 0. Okay, so in reverse bias means what? The P type, this is N type. The P type is connected to the negative and the N type is connected to the positive of the battery. So this is what you have to remember. So with this idea in mind, that means in the forward bias we have a current and in reverse bias no current. Okay, so we will explain one of the important application of the diode. That means we are going to explain the rectifiers. So what is rectifier? Rectifiers are the devices, I can show with a block diagram. Okay, you will give an AC voltage as the input and you will get the DC voltage as the output. Okay, that means you can convert the AC to DC. Okay, this is nothing but the rectifiers. So what I am going to explain is there are different types of rectifiers. You can classify the rectifiers into basically two different types. That means you can have half wave rectifier, first one, and the second one is the full wave rectifier. Full wave rectifier. Okay, and the third and the full wave, actually you have two types basically. One is with sender tapped transformer. Okay, I will with sender tapped transformer. Okay, and bridge rectifier. Okay, bridge rectifier. So you have two types of rectifiers basically. You have the half wave and full wave, and the full wave are of two types. That means you can have A and B, two types. One is with the center tapped transformer and another one is the bridge rectifier. Okay, so first of all we will explain about the half wave rectifier. So half wave rectifier. So what do you mean by half wave rectifier? Usually it is denoted by HWR, half wave rectifier. So you have a half wave rectifier. You will give an AC input like this, sinusoidal wave. This is the time and this is the voltage. Then the output will be something like, you will get only this is the positive part, and you can see the other part is the negative part of the voltage. So you will get only the positive part. That is the main beauty of this. You have the positive part here and this is the positive. So at the output you can see only the positive part. That means you are getting the half of the wave. That is why we are calling half wave rectifier. Okay, half of the wave. That means this is the voltage output, V out of T. This is V in of T. Okay, input, and this is the output. Okay, so how we can design this? You have a load. You should have a load. This is the RL and this is the ground, and you have an input which is given like this. So you have to connect the diode like this, and your input is this one, positive, negative, positive, negative, like this. And you will take your output from here. This is your V out, we will say V out, and this is V in. So this is your V out. Okay, now what will be the output? You will see during the positive half cycle, you can see that this is the positive half cycle. During the positive half cycle, this is positive and this is negative. Now you know that this diode is having P here and N here. Now you see the P is connected to the positive. That means the diode is forward bias. When the diode is forward bias, the diode act like a switch. That means the diode is on. The diode is now on. That means it act like a short circuit. But we are considering the practical model. So the diode will be having a voltage drop across it of 0.7, and we will get a current and we will get an output like this, because it's acting like a short circuit. The diode is acting like a short circuit with a voltage drop of 0.7 volt. But during the negative half cycle, you can see here, during the negative half cycle, the polarity of the voltage will change. That means this end become negative and this end become positive. Now you see the positive, the P type is connected to the negative. That means the diode is reverse bias. When the diode is reverse bias, the diode is now open circuit. That means there is no current. So there is no voltage drop across the RL. The current is 0, I equal to 0. So the voltage output also will be 0. Next cycle, you know, again we are getting a positive. So again you will get a positive here, right? That's how we can construct. But you see here, I am giving a small voltage here, but usually we will be using the half wave rectifiers and full wave rectifier for generating the DC voltage. Why we are saying it as DC voltage? Because the current is not alternating. Here you can say the value of the current is changing, or it's sinusoidal, partially sinusoidal, but it is not changing the direction. The direction is always positive. So the direction is always positive, always positives. Okay, that's why it's we are calling it as a DC, but it is not a perfect DC. So this is not a perfect DC, but we will study how to make a perfect DC later. So it's not a perfect DC voltage. Okay, there are some problems with this DC. It is pulsating DC. It is having some pulses. You can say it is a pulsating DC actually. Pulsating DC, it's a pulses, but all these pulses are positive. That is the benefit. Now we will see how we can make this by using if you have a very large voltage, how we can manage this large voltage and make a small voltage DC. So first of all, we have to convert the large voltage into a small voltage by using a transformer. So you have a input voltage like from the power supply, as you know, maybe for example 220 volt, 60 hertz, like this. Okay, so what I am going to do, you have a voltage input as a function of time, a sinusoidal voltage, something like this. It's a large voltage. So I will use a transformer. This is the symbol for the transformer. You can see there are a lot of windings here for the transformer. This is the primary of the transformer, and this part is the secondary of the transformer. So you are using a transformer. You can see a lot of windings are there on the transformer, and the number of windings on the primary, this is the primary windings, and this is the number of windings on the secondary. So we will call this secondary windings. So the transformer is usually represented with a ratio. Transformer, okay, is usually represented with the number of primary to the number of turns in the secondary. Okay, so you can see this is your voltage V in primary. You can say V in primary. So you will get here some voltage. This is known as V in secondary as a function of time. How to calculate this V in secondary? V in secondary is equal to V in primary as a function of time multiplied with the number of turns in the secondary divided by number of turns in the primary. This is how you can calculate the voltage across the secondary. Suppose example, if n secondary is equal to 10 and n primary, number of turns in the primary is 100, then the voltage at the secondary will be V in primary into 10 divided by 100. That means this will cancel. Your voltage is only 1/10 of the primary voltage. That means if you are giving 100, if you are giving here 200 volt, this will become just 20 volt. That is how you can reduce the voltage. Okay, so this is the transformer. Okay, so next we have a load. I told you we have a load RL, and I will put a diode like this. You see here, this will be this is known as the half wave rectifier, and we will take our output from here. Okay, V out. Now we will see what will be the equations related to this and how it works. Now you have during the positive half cycle, you have the voltage like this First of all, you have the voltage like this. Okay, so during the positive half cycle, that means this is the positive half cycle. So you can assume that the polarities are like this. This is positive and this is negative. Since this is positive, you can assume this is also positive and this is negative. Now you see this is the p-type and this is the n-type semiconductor. The p-type is connected to the positive of the battery. That means the diode is forward bias. When the diode is forward bias, you know that the voltage across the diode will become 0.7 if we are assuming a practical model for the diode. Now there will be a current also. The current will flow like this and it will complete the circuit. So you can see here there will be a voltage drop across this. Okay, that means you can see this is positive and this end become negative. That means you are getting an output which is can be represented using like this. Okay, and during the negative half cycle, we will see during the negative half cycle, that means you have a negative half cycle and this voltage become negative and this voltage become positive. So this become negative and this become positive, but the negative when connected to the P, the diode is reverse bias. When the diode is reverse bias, the current will be 0, so the voltage will be 0. That's it. Okay, so this is the, again in the positive half cycle you will get the output. Now we will talk more about the type of the input. So this is the time and this is the voltage V out. Then what will be the magnitude of this guy, this peak magnitude and all, so that we are going to analyze. So I will draw the circuit diagram again. So this is your V primary of T, or V in primary, you can say V in primary of T, and you have the transformer, and V in secondary of T, V in secondary of T, and now you have a diode and you have RL, and you are taking the output across the RL. This is V out of T. Okay, this is what the rectifier. Now V in primary I can represent like this. This is my V in primary, right? So this is my V in primary of T. Now I will call this voltage the maximum voltage at this point, that is known as VP primary. Okay, maximum voltage. Now what will be my V secondary? My V secondary will be some voltage like this. Same thing, positive, negative, positive and negative. This is positive, negative, positive and negative. This is V in secondary as a function of time. And the maximum voltage, I will call this voltage as VP secondary. Okay, VP secondary. So you know that what is the relation between the primary and the secondary. So you can find VP secondary will be equal to, you know, this is number of turns in the primary is to number of turns in the secondary. So VP secondary is VP primary multiplied with VP secondary divided, sorry, not VP, multiplied with number of turns in the secondary divided by number of turns in the primary. So that's how you can find it. Now you know during the forward bias, I told you during the forward bias, that is plus minus and plus minus here, you see here this, there is a voltage drop of 0.7. So you can say that this voltage is here, it is V in secondary. So what is the output voltage V out of T? That is the question. I can write the Kirchhoff law here. So I am starting from here. So minus V in secondary of T plus 0.7. Then the current is going down during the forward bias. So plus V out of T, this is equal to 0. That means my V out of T is nothing but V in secondary of t minus 0.7. That means that the diode is actually taking 0.7 volt and the remaining voltage will be dropped across the load resistance. Okay, so Vp secondary also, sorry, V out maximum or Vp out, you can say P for peak. So the voltage output will be like this. I told you already, the voltage output will be like this. Okay, now what will be the maximum voltage at this point? That is our question. That is known as Vp out, maximum at the output. So Vp out is equal to Vp secondary, okay, because you will take this equation. So Vp secondary, sorry, not this equation, we will take this guy, okay, we will take this equation, Vp secondary minus 0.7, that's it, okay, because V out is nothing but V in secondary minus 0.7. So Vp out is Vp secondary minus 0.7. Now if you know, so Vp out is equal to Vp secondary minus 0.7, and this is your output, positive, and this is Vp out. Okay, now if you know Vp out, you can see that the average voltage, that means the average, this is the maximum voltage and this is the minimum voltage is 0. So there may be some average voltage also. You can calculate the average voltage, it may be somewhere in between. And what will be this level? This you can directly use the formula that you have studied in Dawair Kaharbai. That means the V average is nothing but the maximum voltage, maximum V max divided by pi. But what is V max at the output here? You can see that at the output the V max is nothing but Vp out. So Vp out divided by pi. So this is how you can calculate the average voltage. We will call this average also as it is the DC voltage. Okay, now that is the average voltage. Now there is one more phenomenon, that is one more parameter. It is nothing but the peak inverse voltage. Okay, it is nothing but the peak inverse voltage. Peak inverse voltage. Okay, peak inverse voltage. What is this? We will talk about this thing. You have the circuit like this. This is your RL. Now this is your output, V out. Okay, now you know that during the negative half cycle, that means whenever in the negative half cycle you will get a negative and positive, this is negative and positive, the diode is reverse bias. That means the diode current is 0, that is your diode is acting like a open circuit. Okay, so you can see the maximum voltage across this, we can call it as a Vp secondary, but the direction is like negative here and positive on the other side. So this voltage cannot make a current, and the voltage drop across this, is actually 0 volt, you can say. So all this voltage will be dropping, will be across, not dropping, all this voltage will appear across your diode. That I am going to show. You can see here all this voltage will appear across the diode. The diode is open circuit. This is your diode, and there is no voltage drop here. So whatever you are applying here, Vp secondary maximum voltage, I am talking about the maximum voltage, all this will be appearing across the diode, and this voltage will be nothing but Vp secondary. So this voltage, that means the maximum voltage maximum voltage appearing across the diode during the reverse bias, because this will happen only in reverse bias. In forward bias, the diode is short circuit. So whenever the diode is open circuit, that means the diode is open circuit, is called, this is known as the peak inverse voltage, which is PIV. So this is known as the peak inverse voltage. And what is the relevance of this? Suppose you are making a rectifier, and you have a diode, and suppose the maximum voltage which is appearing across the diode was suppose it is 20 volt. Then your diode should have an ability to resist this 20 volt. Suppose you choose a diode which is having a ability of 25 volt, and you are giving a maximum across the diode. Now it is coming, you can say the maximum across the diode may come is only 20 volt, and your diode can block up to 25 volt. This is okay, it will work. But if you buy a diode which can block only 10 volt, and this is the capacity of the diode, this is the capacity of diode to block, or ability to block, but you are giving only minus plus this 20 volt, and this your diode can block only up to 10 volt. What will happen? The diode will act like a short circuit. It cannot block the voltage, it cannot block the current. That means it has only a resistive power, it is having only a blocking capacity up to 10 volt. So you can, according to your design, you can choose this. So if you are designing for a particular voltage, then according to that you have to choose a particular diode. So this is the half wave rectifier. I hope that you understood this. Thank you.